Okay, so we're going to talk about evaluating limits. Analytically. This is probably the simplest thing that you will ever do in calculus. Because when you're evaluating limits analytically, this is just telling you all of the times that you can take the function and plug the number in and get the answer. These are the cases where, you don't have to write this down, where it's the graph and the function are, or the graph is doing the same thing at the point as around the point. It's just a pretty function. These are basically all the pretty functions where all you have to be able to do is plug the number in. I'm going to give you the page numbers in the book if you want to specifically look up the rules that they give you. It's 1-3. I'm not sure I would even look at the rules. It's the first thing that you want to do when you're trying to evaluate a limit, okay? Anytime you're given a limit, the first thing you try is you try to plug the number in, and you keep your fingers crossed that it works. If it works, great, and you're done. If it fails, then you have more work to do. But today, we're just talking about all the places where it is definitely going to work, okay? So if you look at page 59 in your book, if you took an actual book, if you have the digital version of the book, I think you can still look it up by page, otherwise we're in 1-3. It's 59. A few things you have the limit as x approaches c of b is b. What that means with an actual function, if you have the limit as x approaches, say, 7, doesn't matter what you're approaching, 7 is going to be 7 until the end of time, okay? Another one, limit as x approaches c of x equals c, fine. So if you've got the limit as x approaches 3 of x, you're plugging in 3 for x, you get 3. I cannot emphasize how much you need to not overthink this, okay? Limit as x approaches c of x to the n is c to the n. So if you're looking at the limit as x approaches 2 of, say, x to the 4th, that would be 2 to the 4th, which is 16. You can also do scalar multiplication, sums and differences, products, quotients, powers. So some examples of those. So you've got the limit as x approaches 3 of f of x. They told you it was 7. And the limit as x approaches 3 of g of x is 4. And then they want to talk about scalars and things like that. So if it's scalar multiplication, that would be like 2 times f of x. Well, okay, if you know that the limit as x approaches 3 of f of x is 7, then 2 times that would be 2 times 7, so it's just 14. The limit as x approaches 3 of f of x plus g of x. Same deal, you're just adding that one and that one and then with 11, okay? Again, notice, it's this whole thing that equals 14 or the whole thing that equals 11. It's not just this part. That on its own is an operator. It's kind of like the sine of something or the cosine of something where you can't, on its own, make it equal to anything. That's not how math works, okay? Let's do powers. So if you're trying to cube g of x, you know g of x is 4, you're cubing 4, and then you get 64, okay? If you look at page 60, They talk about polynomials. Polynomials work the same way. The reason that you can just plug into polynomials is because they're nice, pretty functions that don't do anything freakish. So if you have a polynomial, you can just plug into it. There's your function. You want the limit as x approaches 3 of f of x. It's not always 3. Apparently I use 3 a lot. It's the same as just finding f of 3. And plugging in 3. Then you got what? 9 and 3 and 1, say 13. You can also do this with rational functions as long as your bottom's not 0. So if you want the limit as x approaches 2, doesn't make the bottom 0, which is good. If it did make the bottom 0, you'd have to do other stuff, but that's a different lesson. So it's the same as f of 2. So then you just plug in 2. So if you plug 2 into the top, you get 7. If you plug 2 into the bottom, you get 8. Done. Again, please don't overthink this day. This should take you like no time to get all these done, okay? You can also do radical functions. Say f of x is the 5th root of x. And you want the limit as x approaches 32 of f of x. You want the 5th root of 32, which is 2. That's it. You're just plugging it in. Okay, so again, if you wanted to, you could write it's the same as f of 32, but you really don't have to. You can also do composite functions. So if you want the limit as x approaches 2 of f of g of x, fine. That means that you're doing f of the limit as x approaches 2 of g of x. You pop it in there. The limit as x approaches 2 of g of x is just the same as g of 2, so 2 cubed. So really all you're trying to then find is f of 8. So then f of 8 is going to be negative 3, okay? This also works for trig functions, and the composite functions are on page 61 if you want to look at them, but really it's just saying the same thing, plug in number now. So the trig functions work as long as you're not looking at one of the asymptotes. Make sure if you're evaluating a trig function that you give an exact answer, okay? Don't type it into your calculator and give me the decimal approximation. That's not going to work for me for trig functions. You got to make sure you're exact about it. So, if you want the limit as x approaches pi over 4 of sine of x, you'd need to figure out what sine of pi over 4 is, which in theory you know. If you don't know, you need to re-pick up how that works. So sine of pi over 4 is going to be root 2 over 2. Because that's what you can actually evaluate, you should know. Let's say that you wanted the limit as x approaches, I don't know, 6 of cosine of x. 6 is not one of the special things on the unit circle because it's 6. So this would just be the cosine of 6, and that's as exact as you can be. which is fine, okay? You can't leave it something like the sine of pi over 4 because this is a thing that you're supposed to know, okay? You don't know the cosine of 6 off the top of your head. So leaving it like this is fine. This is unacceptable. You have to evaluate it. This would be okay, all right? And really, that's it for evaluating analytically. Just plug the numbers in, okay?